For the one for
the homework. It's like some freezer.
the rectangular one?
Yeah. Because it's just like. There's the outside the treatment.
It's like a whole day ago.
Yeah. See,
Okay, so you know how that problem mentions is problem mentions this boundary.
yes.
So I was like, I think you had
It's like right here. But the thing is that you have this and then this and then the temperature.
okay. I didn't include them. I have them in the equation, but I took them out because they're not mentioned. I see what you mean.
Yes,
They don't matter.
Right here's the. Does it even so
They give you the temperature, but you don't know what each is.
I can see like you have two different formulas right here. Right? This one includes the temperature outside. And then you have also this one right here. And you're like, well, which one do you use? You know, like what are the key words? Or does this one like code specifically like this one?
I feel like today, if it goes into the again,
Yeah,
it's better and easier to ask one question.
that's what I'm on.
Well, so
Yeah, definitely.
it's like there's a lot of these things that we haven't talked about. Like, I don't know if they did them.
Pretty long. I don't mind gambling. Like I'm certainly, I feel like a lot of my thought I'm doing is kind of like roll the dices.
Yeah.
I'm just like, you know, yeah. I think this is it.
Do you have an answer for that?
For which one?
For the one, 31?
No, because pretty much I'm not sure if to go with this one or this one. What makes these two, this is a special case. Cause like they look both the same, just that. Why do you give us the outside temperature and this is an enclosed one? That's it. And if you actually draw it, there's like a steel inside and then aluminum. And then you have temperature outside. And also you have another. There's a heat transfer or heat flux inside. Right? So it's just like, what the hell? Like,
That's what I'm saying. Oh, so, okay.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good. Great crowd today. All right, so today, we did a little bit of a sneak preview last week just because we finished a bit early, but the subject for this week is going to be 2D finite elements. And so basically, we're going to start with just diffusion, and then we're going to move on to convection probably on Wednesday. But we'll see how things change when you go to 2 dimensions, right? The basic idea is not going to change, you'll see. So, we're still going to be applying finite differences to our equations. We're going to be writing a bunch of algebraic equations, and then, writing those out. What's going to be different is you'll see there's a lot of additional bookkeeping that comes with doing problems in 2D. And this week is a little bit, you may have noticed this, but a lot of the notes that I'm using for this class right now are taken from another class that I teach, which is EGME 417, computational heat transfer. But in that class, I focus a lot more on the MATLAB programming. This time I'm not. So there's going to be a lot of things in the lecture notes which refer to the MATLAB programming, but we're obviously not going to do that in this class, but it is still important to know kind of what is required, to have kind of a 2-dimensional mesh like this, because a lot of those concepts are used in OpenFOAM. So I think if you have a good grasp of what these concepts are and why they exist and why we need them for a mesh like this, then I think it really helps to understand a lot of what we do inside OpenFOAM. Okay. All right, so the one announcement I have to make is that I did post homework 2. No, I'm aware that homework 1 has not been turned in yet. So homework 1 members due this Wednesday. But I did want to post homework 2 just because I know quite a few people have finished homework 1 already. So homework 2 is due actually next Friday. So you have about a little bit less than 2 weeks to do homework 2. It's basically going to be a lot of these 2D stuff, a little bit of convection stuff. So it shouldn't be too much of a big step up from homework 1. Okay. So just be aware, homework 2 is due Friday, February 20th, just next Friday. Any questions I can answer before we get started today? Okay. All right. So let's go and get started. Get my pen out of here. Okay. Okay. So the topic for today is 2D finite difference problems. Okay. And by the way, in this class, we're stopping at 2D, because the jump from 1D to 2D, I would say is pretty significant just because we have to introduce a lot of new concepts going in multiple dimensions. But going from 2D to 3D is not as big of a jump. And so I'll discuss when 3D is appropriate, but you'll see that we use a lot of the same conventions. It's just more of this stuff. Okay, so let's kind of recap where we've been so far. So far we've applied finite differences to solve 1-dimensional differential equations with diffusion and convection. Our equations look something like this. And so we had, maybe a convection velocity like that, and that's equal to d squared phi dx squared. Maybe there's a diffusion constant k plus some source term. Okay. All right, with the biggest limitation obviously being in 1 dimension. So we only were able to solve equations where, we only had 1 spatial dimension in x. Okay. So if you think about homework 1, right? our solution domains were limited to basically just straight lines. Which is fine, right? And so, we all have to start somewhere. And typically, you start with one-dimensional problems, but of course that really limits what you can apply your tools to, because there's not very many one-dimensional problems out there in reality. Okay. Okay, so as we add dimensions, typically what happens is that we add spatial derivatives in those dimensions. Okay. Okay. So we go from 1D to 2D to 3D. Okay. Okay. So that's, I think, the most obvious thing that you'll notice is that, our equations get more complex, right? We add more derivatives. And instead of, ordinary derivatives, we start to have partial derivatives. Okay. Okay. So for example, right? So if we look at the 2D diffusion equation, right? So we're gonna ignore convection for now. So we'll bring back convection. We'll probably talk about it more on Wednesday. But if you just look at the 2D diffusion equation, it looks something like the following. So you have partial squared phi, partial x squared, plus partial squared phi, partial y squared is equal to, we can add a source. So let's say we have a source term as a function of x and y. Okay. Right, so we have our derivative in x, derivative in y. In this case, we're adding them together, and that equals a source term. Okay. And then we can look at the same equation in 3D. Okay. Where you can probably guess what we're going to do. We're going to add a z derivative to this equation. Okay. All right, so more derivatives means that we have more terms, more finite differences we have to apply. The good news is that our general approach doesn't really change, right? And so at this point, let's say that we wanted to solve this with finite differences, we do it in the exact same way we did in the 1D equations. We just take every single derivative and just replace it with the finite difference approximation. Okay. Okay. And in fact, the formulas that we use for the finite difference approximation don't really change. So here we have all second order derivatives, and so we're going to use this exact same second order, finite difference approximation for the second order derivative. Okay. The only thing that does change is that you're changing the direction, but that's usually kind of a minor thing. Okay. So up until this point, it's not too different, right? But what is different is the fact that our domains now are going to be a lot more complex. Okay. Okay. Right. And that's typically a good thing, because in 2 dimensions you have a lot more freedom in terms of what kinds of domains that you want. Because in 1 dimension, we don't really have any variety. You can either have a long line or a slightly shorter long line, right? And so but in 2 dimensions, we have the concept of shape that we can do too, right? And so the very basic one is we can have maybe just a square domain, right? We can have an L-shaped domain, right? Right, we can have a U domain. Okay. Okay. Right, we have basically a lot more options, and then we're starting to get into the realm of we can actually do a lot of really practical problems with 2D flow as well, right? And so the third dimension isn't always strictly necessary. So there's a lot of really interesting things you can do. Like you can do flow over an airfoil with the 2D simulation, and that's perfectly perfectly valid. Okay. Now, with greater complexity does come greater challenges, right? And so, being able to kind of manage these domains and kind of keep things organized, that's kind of where the challenge is. Okay. So I'll just kind of put an umbrella term over it where, the challenge with 2D and 3D is more on the bookkeeping. Okay. And you'll see that even for a very straightforward domain, even for a square domain, there's a lot more that we have to do, in order to kind of stay organized and making sure our equations are correct, compared to the one. Okay. And then by the end of this week, on Wednesday, we'll introduce this concept of what's called an unstructured grid, which is kind of the standard in terms of computational meshes nowadays. And we'll talk about kind of what's required for them. Okay. So in general, OpenFOAM uses unstructured grids, and so it's very useful to kind of know what that means. Okay. Okay, so that's where we're going this week. So it's less about the equations and kind of more about the domains this week. So kind of a shift in focus, but we're still going to end up in the same place. We're still going to end up with algebraic equations that represent our our differential equation. Just a few more steps to get there. Okay. Okay. Any questions on this so far? Okay. Good. All right. So let's do some basics. Okay. So let's do. Let me just do a square domain for now. Let's put a grid on this, and so let's put a waffle. All right, so this is kind of the simplest two-dimensional domain that you can come up with. Okay. And let's define some variables that we use here. Okay. So since we're in two dimensions, we need multiple variables to describe the size of our domain, right? So, for a very simple square domain like this, at the very minimum, you need Lx, which is the length of the domain in the x direction, and then Ly, which is the length of the domain in the y direction. Okay. Okay. Note that Lx and Ly are always given in some kind of physical measurement, right? So, for Lx and Ly, we're talking like 1 meter, 2 meter, 3 meter, right? So this is the physical measurement. Okay. So Lx and Ly are kind of independent of the grid, right? And so, whatever physical situation you're modeling, doesn't really matter how many grid points you're using, the size of the domain is the size of the domain. Okay. Okay, another quantity that you need to know is Nx and Ny Now, NX and NY are used to describe this specific case of a 2D grid, but or excuse me, a square domain. But if you had a more complex domain, it would be you probably need some more measurements. But in a very simple sense, NX and NY describe how many grid points that you have in each direction in your grid. So, for this case, we can just simply count. And so if we look at NX, right? So we look at how many grid points are in the X direction. So let's count 1, 2, 3, 4, 5, 6. Okay. Right. And so for this particular example, we say that there are 6 grid points in the X direction, right? And then in the Y direction, we have 1, 2, 3, 4, 5. Okay. Okay. So NX and NY can be the same. They don't have to be the same, but but that's something to keep in. Okay. All right. So now that we have LX, LY, NX, and NY defined, we can now use those to describe the grid spacing. Okay. So in general, for this class, we generally assume that the grid spacing is uniform. So we don't have any non-uniform grids. We will talk about how we deal with that on Wednesday. But for now, we can assume the grid spacing is going to be the same in every uniform throughout the grid. So the definition of the grid spacing is the exact same as our 1D problem. So the grid spacing is nothing more than just the physical distance separating the adjacent nodes. Right. So we're going to have the same grid spacing in the X direction. So in the X direction, we'll say our grid spacing is delta X. That's nothing more than just the length of the X domain divided by NX. And we're going to subtract 1 because, so if we use NX to define the number of grid points, then the number of grid spaces is NX minus 1, right? Because if you count the amount of grid spaces in the X direction here, right? So we have 1, 2, 3, 4, 5, right? So the grid spacing is going to be LX divided by the number of spaces, which is NX minus 1. Okay? And then the same thing for delta Y too. So delta Y is equal to Ly divided by Ny minus 1. Okay. Okay. So those are just kind of basic definitions. So I'll be referring to these variables, Lx, Ly, Nx, Ny, grid spacing. So it's useful to kind of have these. Okay. All right. Any questions on this so far? Okay, good. All right, so let's get to kind of the first kind of big topic, which is node numbering and node labeling. Okay. Okay. All right, so how you label the node numbers is basically of really critical importance for 2D problems. Okay, so let's start by saying that every node in a finite difference grid has to have a unique ID number that's unique to that node. Okay. Right, it's exactly the same as the 1D domain, right? So it's just that in the 1D domain, it was very kind of straightforward, right? So if you look at our 1D domain, right, or 1D grid, right? We had our line broken up into, smaller lines. And the node numbering was something that we didn't really pay too much attention to just because there was really kind of only one obvious way to do it, which would be to number them from left to right. Okay. But for a 2D grid, it's a bit more complicated because we're going kind of up in dimension, right? And so for 2D, I'll give you kind of a very basic numbering scheme. Okay. So let's say we have a 2D grid like this. Right. So on a basic level, you can start in the bottom left, right? And you can label the node numbers going left to right. So we have node 1, node 2, node 3, node 4, node 5, node 6. Okay. And then we just go to the next row. So we have node 7, 8, 9, 10, 11, 12, right? 13, 14, so on and so forth. Okay. Right. So that's one way to provide the node numbers. Okay. So you just basically you start in the bottom left, you go left to right, and then when you reach the end of the row, you just go to the next one. Okay. But of course, in 2D, that's not the only way that you can number it, right? So you can go up the columns instead. Okay. So let's say another node numbering scheme would be like, I'm going to use purple for this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Right. So that would be another way that you could number the nodes. Okay. So it doesn't really matter which numbering scheme that you use. The only thing is that you kind of stay consistent. Okay. So once you kind of establish a numbering scheme, you want to make sure you kind of stick with it because you're going to refer to those nodes by their numbers. All throughout your equations. Okay. I will say that I prefer the scheme that's the kind of the first one that I wrote up here where you go from left to right. And so all the homework problems where I give you a grid, they're going to be numbered in that way. But just know that if you're defining your own problem, you can use whatever numbers you want. Okay. So that's the ID labeling. Okay. The other thing that's important to note for these is, excuse me, is you need to know the node indexes as well. Excuse me. Okay. So every node must also have a unique IJ index. And for that, you could kind of think of your grid here as kind of like a Cartesian coordinate. Okay. All right, so let's draw our grid again. Okay. But instead of the ID numbers on these nodes, I'm going to draw in their IJ coordinates. Okay. Okay. So if you think of each node as kind of being its own, like point on an XY Cartesian grid, right? You can come up with an ordered pair to describe its index. Okay. And then you go to the second row, we increment the J index now. So this node would be 0, 1. This would be 1, 1, 2, 1, 3, 1, 4, 1, 5, 1. Okay. And so on and so forth. Okay. So the point of the IJ index, and you can see that we're only going up by integers, right? This tells you, which node or how many nodes that you traveled in that specific direction. Okay. Okay. So for instance, if we look at this node right here, right? The IJ index for this one is the 3, 0 index. Okay. So this tells us is that the location of this node in the grid is that this is the third node in the X direction. Well, I guess technically it's the fourth node because we started numbering at 0. Okay. Sorry, let me go ahead and change that. This is the fourth node. Okay. And then in the Y direction, we're kind of on the base layer. So this is the first node in Y direction. Okay. All right. So the IJ index, this is going to be important because you'll see that when we actually start to apply our finite difference approximation to our differential equations, we're going to do those, or the way we're going to label the nodes in that equation is by its IJ index. Okay. Okay. So it's useful to know kind of what the IJ index is. Okay. All right. Good. Right. So every single node in a 2D grid has to be assigned a unique ID number. So that is a number that counts from you start counting at 1 all the way up until the number of nodes in the grid. And every node also has an IJ index, which tells you kind of it kind of tells you more its location within the grid. Okay. Any questions on this so far? Okay. So we have these kind of two systems of numbering, right? An ID number and an index, right? So one thing that we always going to have to do for any 2D or 3D problem is you have to be able to convert in between these two, in between these two different labeling schemes. Okay. Right, and I will say that for the problems that we're going to be doing in this class, this conversion is going to seem very silly because most of the time you can just look at the grid and determine who the neighbors are, what their ID numbers are, what the IJ index is, and so for simple problems, this is kind of overkill to have equations for this and schemes for this. But it's the reason we have these schemes is for kind of more complex problems where you can't just look at the mesh and determine these things. Okay, so basically, it would be nice if we had an equation that converted, from one to the other. Okay. All right, so the conversion that's used most often is that we go from the IJ index and we use that to compute the ID number. So there should be kind of a very straightforward conversion, right? Because every node, right? We've already kind of established that every node in your grid is going to have a unique ID numbers, but also every node in your grid is also going to have a unique IJ index, right? So there's going to be no node with the same IJ index as another node. You know, because you can't have two nodes on the same location. Okay, so it should be pretty straightforward to convert between, you know, let's say that you're given an IJ index for a given node, you should be able to compute what its ID number is for that given node. Okay. All right, and so in fact, you know, we do have a very simple equation for it. Okay. So ID is simply J minus 1 multiplied by NX plus I. Okay. So in here, I and J, those are the IJ indexes for the given node. So you plug that into this equation and that gives you your ID. And I guess technically, if we're starting our ID number from 1, we should add a +1 to that as well. Okay. Actually, I apologize. It should just be J. I'm going off a little bit different from my notes because I'm starting IJ at 0. So this should just be J times NX plus I plus 1. I apologize because for the IJs we're starting at 0, but for the ID numbers we're starting at 1. Okay, but of course, you know, this does kind of commit us to a particular ID scheme. So this equation only works if you're using a left to right ID numbering scheme. But basically, the scheme that I kind of outlined for you before, where you start at the bottom left corner, you start numbering from left to right, and then when you go up to the next row, you go from there. Okay. So using this is very straightforward. So, you know, let's do a couple of examples. All right, so let's use this grid up here that I've kind of already kind of drawn, right? So let's use this equation to compute, you know, let's compute the ID number for this node right here. Okay. So for that node right there, you know, our I index is 2. So we're going to compute ID number for node I equal to 2, J equal to 1. Okay. Okay. And so we just plug into the equation from there. So if ID is equal to, we have J is 1 multiplied by NX. And so the number of nodes in the X direction, we should have 6. 1, 2, 3, 4, 5, 6. Okay. Okay. Plus I, so I in this case is 2 plus 1. Okay. All right, so we just do kind of the simple arithmetic, which is 6 plus 2 plus 1, that's 6 plus 3, which is 9. Right, so that particular node there should have ID number 9, right? So let's just kind of go up and verify here, okay? So let's circle that same node here, which is this one right here. And that node does indeed have ID number 9. Okay. Okay. So again, you know, I know it seems kind of trivial and kind of silly to have an equation for this, but, you know, when you can just look at the mesh and kind of see it. But you can actually do some interesting things with this equation here, you know, especially, you know, if you're going to be doing this, you know, with programming and things like that, right? So the most common application for this equation is that, you know, oftentimes when you're writing your finite difference equation, you're going to need the ID numbers for every single neighbor of a given node. Okay. So first thing, if you're tasked with finding the neighbors of a node, right? The IJ indexes kind of work really well for this, right? So for a given node, I comma j, right? And let's assume that this I comma j is somewhere in the middle of the grid. So we're gonna have neighbors on all sides, right? We'll deal with the boundary conditions later. And so, obviously there's going to be exceptions for, when we're at the boundary. But let's assume for now that we have a neighbor on all four sides. Okay. Okay. So first thing you usually do when you're trying to find the ID numbers for a given neighbor is you find the IJ coordinates first, right? So the left neighbor is very straightforward. You basically take your IJ of your central node, and your left neighbor is going to be the one to your left. And so that's going to be I minus 1, right? So I minus 1, comma j. Okay. The right neighbor is going to be 1 to the right, and so that's going to be I plus 1, comma j. Okay. Top neighbor is going to be I, comma j plus 1, because that you're going up in the y direction. And then bottom neighbor is going to be I, comma j minus 1, because you're going down. All right, and so all of those you can compute pretty easily, and then you can take each one, plug it into your ID equation. Okay. And that'll give you the unique ID numbers for each of those nodes. Okay. And you're going to need those ID numbers because when we write our finite difference equations, typically you don't write them in terms of I comma j. You typically write them in terms of the ID. Okay. And the reason for that is that those ID numbers kind of signify to you which row in your matrix that you're going to be affecting, right? And so that's why you use that. It just makes the programming a lot more easier if you're going to build based on the ID numbers. All right. Any questions on this? Okay, one more concept before we actually get to the finite difference, right? So we've talked about the ID numbering scheme. We talked about the IJ indexing scheme. There's one more actually labeling that you have to know, and that's mostly just for computing certain things in the equation, which are the physical coordinates of each node. So the physical coordinates we usually denote xi and yj. Okay. Now the good news is that the physical coordinates are usually pretty straightforward, especially if you are assuming you have a uniform grid, right? So let me go ahead and kind of draw our grid one more time. Okay. So to find the physical coordinates, basically you're just going to basically just multiply the ij coordinates by the grid spacing in those particular directions. Okay, so for example, let's say that we want to find the physical coordinates for this node right here. Okay. Okay, so first thing we're going to do is we're going to find the ij coordinates for this, and so this is 0, 1, 2, 3, 1. Okay, so ij coordinates for this are 3, comma 1. Okay, And so the physical coordinates xj or xi, excuse me, xi is just going to be 3 multiplied by the grid spacing in that direction. So 3 times delta x. Okay. And then yj is going to be the j index, which is 1 in this case, multiplied by delta y. Okay. All right, so you're not going to use the physical coordinates in every problem, but there are certain source terms. I gave you some problems like this in homework 2, where you do need the physical coordinates to compute the equations, right? And so that's how you compute. Okay. You use the same concept in 1D problems as well. I think we did actually use it in one of the examples we did last time, but I do want to kind of be explicit with it in 2D. Okay. So when you're given an equation and you have, there's an x floating around, there's a y floating around, right? Usually they're going to be in the source term, but you might see them in a coefficient as well. This is how you kind of compute it for any given node. Okay. And obviously every node has a unique physical coordinate as well. Okay. It's just that from a programming perspective, the physical coordinate is not that useful. It's only really useful if it's part of your equation. But I did want to make note of how to compute this, just because I did give you guys a couple problems like this. Okay. Any questions on this? Okay, good. So let's get to actually applying finite differences. Okay. Okay, so let's take our 2D diffusion equation and then let's apply finite differences to each term. Okay. All right, so let me go ahead and write out our 2D diffusion equation one more time. Okay, so we have a second order partial derivative in x plus a second order partial derivative in y of the same variable is equal to the source term q of x, y. Okay, so to apply finite differences, we have basically 2 second order derivatives here. So we're just going to plug in our finite difference approximation, noting, which direction we're going to take the derivative in, right? So that's going to change how we index I and j. Okay, so let's do the x derivative first. Okay, so derivative in the x direction, that means we're going to be doing variations in x, which is the I direction, right? So this is going to be phi I plus 1, comma j, minus 2 phi I, comma j, plus phi I minus 1, comma j, multiplied by the grid spacing in the x direction squared, so delta x squared. Okay. All right, and then for the y derivative, our y derivative for finite difference has the exact same form, except we're modifying the index in j, because we're taking derivative in the y direction. Okay. So this is phi I, comma j plus 1, minus 2 phi I, comma j, plus phi I, comma j minus 1, all divided by delta y squared. Okay. And then for our source term, we can't really do anything with it until we actually know the functional form. But we do know that, usually we're going to evaluate this at the physical coordinates of a given node. Okay, so this becomes q at xi, comma yj. Okay, so using the physical coordinates that we kind of just finished talking about. Okay. All right. So to simplify this equation, typically what we'll do, especially just starting out, we'll assume that we have a perfectly square domain. So that's, equal length in X and Y direction. We're going to assume the same number of grid points. So usually what we're going to do is we're going to assume our grid spacing is the same in both directions. So if we assume, okay, let's assume that delta X is equal to delta Y. Okay. And so usually what I'll do is I'll just replace the grid spacing by just a generic delta, right? So basically assume that the grid spacing is the same in all directions. What we can do is that, if our grid spacing is the same, we can basically factor it out of both fractions on the left-hand side. Okay. So let's multiply both sides by the grid spacing. Okay. Technically, it's grid spacing squared. Okay. Right. And if we do that, and then if we combine like terms, we end up with our, very generic kind of 2D diffusion equation. Okay. Okay, so if we do that, we end up with phi I plus 1, comma j, plus phi I minus 1, comma j, plus phi I, comma j plus 1, plus phi I, comma j minus 1. Okay. So all the neighbor terms, we can't really do anything about because they're all unique, right? But we do have a common term here. So both of these expressions have a minus 2 phi I, comma j. So if we combine those, that becomes minus 4 phi I, comma j. Okay. And then on the right-hand side, we have our source term. That stays the same. Okay. The only difference is that we're multiplying, because we eliminated the grid spacing from the left-hand side, we have to multiply the right-hand side by that grid spacing. Okay. Right. So it looks like a lot of terms, but it is still pretty straightforward because everything on the left-hand side is basically just our central node I, comma j, and all of its neighbors, right? So I plus 1, comma j, this is the right neighbor. I minus 1, comma j, this is the left neighbor. Okay. J plus 1, this is our top neighbor. Okay. J minus 1, this is our bottom neighbor. And then I, comma j, obviously that's our central. Okay. All right. Good. So the 2D diffusion equation is very balanced, right? And so you basically have representation from every single neighbor. And then the application of this is just, same thing as we did before. So we're just basically going to apply this equation to our nodes, right? And then we just kind of plug in from there and then we get our equation, okay? So like I mentioned earlier that, typically when you actually apply this to a node, you don't keep this equation in IJ format. You replace everything by the ID numbers, okay? So let's do an example with actual numbers here. And then let's see kind of how this is typically displayed. Okay. So let's do this grid here. Okay, so I'm going to label all of the nodes here. So 1, 2, 3, 4. Five, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. All right, and then let's say that we have a very basic diffusion equation. So let's say that we have let's say 3 times partial squared phi partial x squared plus partial squared phi partial y squared is equal to, let's say it's equal to 7 times x times y. Okay. Okay. So for this grid and for this equation, right? Typically what you'll be asked to do is given this equation, given this grid, write out the finite difference equations for a certain number of nodes. Okay. So I'm just going to pick 2 of these just for an example. So let's pick node 6 and let's pick node 11. Okay. You thought I was going to say 7, but okay, so let's do the finite difference equation for node 6. So let's first take our differential equation here and let's discretize it. Okay. Okay. So just like we did, in the generic terms, let's replace each of our derivatives with a finite difference. Okay. So we have 3. That 3 there is just going to be along for the ride. So then we have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j all divided by delta x squared, okay, plus phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1 all divided by delta y squared. Okay. And then our source term is we're just going to replace x and y with xi and yj. Okay. Oh, we need our grid spacing. So let's assume a grid spacing. Let's assume a grid spacing of 1/2 in each direction. Okay. Usually for these problems, and just like in the homeworks, I'll give you the grid spacing. So that's not something that you have to kind of assume. I'll usually give you a nice number, so you don't have to do. I won't give you like 0.23 or something. So we'll assume that delta x is equal to delta y is equal to 0.5. Okay. All right. All right, so let's simplify this, right? And so, before we start kind of plugging in node values here, let's go ahead and simplify all the other coefficients, right? First thing I'm going to do is I'm going to take that 3, I'm going to divide both sides by it, okay? Right? And then let's plug in for the delta x, delta y. So delta x squared, 0.5 squared is going to be 0.25. That's also going to be for delta y squared as well. And so 0.25, that's the same as 1/4, right? And so let's put that in. So if I move the 3 to the other sides, we have phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j, all divided by 1/4, okay, plus phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1, all divided by 1/4 is equal to 7/3 xi y j. All right, let's factor out the 1/4 from the denominator. And so we factor out a 1/4 from the denominator, that ends up being a 4 in the numerator, right? So we kind of take the reciprocal of the denominator, right? And so we end up with 4 multiplied by phi I plus 1 comma j. I'm going to go ahead and combine the central nodes. And so, just so that we save me a bit of writing. So we have phi I minus 1 comma j plus phi I j plus 1 plus phi I j minus 1 minus 4 phi I comma j is equal to 7 over 3 xi yj. Right? Yeah.
For the 140, is it the delta x shouldn't be squared?
So the delta x is 0.5, and so when we square it, it ends up 0.25. Yeah. So I'm saying the quantity is it's all right. So last step, before we start plugging in ID numbers, let's just divide both sides by the 4. And by the way, you don't have to, I like to keep the left-hand side clean just because I like seeing the pattern of 1, 1, 1, 1, 4, minus 4. But you could very easily keep coefficients on the left-hand side too. And so, as long as you're consistent in terms of how you're applying the equation, it doesn't really matter where you put the coefficient. Personally, I like to move everything to the right. Okay. Okay, so we divide by 4, then we get bi plus 1 comma j plus bi minus 1 comma j plus bi comma j plus 1 plus bi comma j minus 1 minus 4 bi comma j is equal to 7 over 3 times 4, which is 12 xi yj. Okay. All right, so that right there is our finite difference equation for this particular problem. Okay. All right, any questions on how we got to this point here? All right, good. Okay, so technically, you could apply this to every single node in this grid. Well, I guess technically you can only apply it to the interior nodes. Okay. But let's only apply it to the 2 nodes there, just so we're not writing, for all of eternity here. Okay. So let's apply this to node 6. Okay. All right, and then we're going to write out the finite difference equation in terms of the nodal ID numbers. Okay, so let's go back up to our grid here. Let's look at node 6. Okay. So I didn't write it in, but we can kind of look at this and see what the ij coordinates are for this. Okay. So for node 6 right here, we can see that the I coordinate or the I index is 1, and the j index is also 1. Okay. Let's I is equal to 1, j is equal to 1. Okay. And then we can also use this to compute the physical coordinates as well. So xi, remember, is I multiplied by delta x. Okay. And so we know delta x is 0.5, so that means xi is going to be 0.5. And then yj is going to be j multiplied by the grid spacing in the y direction, which is also 0.5. Okay. And so if j is equal to 1, that means our y coordinate is going to be 0.5. Okay. All right, and so let's just start plugging it in. And so, one way you can do this is, you can plug in the ij into every single term here, right? And so we'd have phi I plus 1 comma j, so that's phi 2 comma 1 plus phi I minus 1 comma j, so that's phi 0 comma 1, and then phi 1 comma 2, so that's j plus 1, and then phi 1 comma 0, okay, so that's j minus 1 minus 4 phi 1 comma 1 is equal to 7 times 7 over 12 multiplied by 1/2 multiplied by 1/2. And so that is 7 over 12 times 2 is 48. Okay. Okay. And so from here, you can take every single ij coordinate in here and then plug it into your ID equation, and then get your ID numbers for each of these nodes. Okay, that's one way you can do it. But for these simple problems, and because we're not going to be doing the programming, I would say just go visually off the grid. Okay, because we know, right? We know that I plus 1 comma j, this is our right neighbor, right? I minus 1 comma j, this is our left neighbor. J plus 1 is top, and then j minus 1 is bottom. Okay, so let's use that information. So for node 6, let's go up to node 6 here, right? We can see that our left neighbor is node 5, our right neighbor is node 7, our bottom neighbor is node 2, and our top neighbor is node 10. Okay. Okay, and luckily for a 2D diffusion equation, it doesn't really matter what order you put the neighbors in, they all have a coefficient of 1. Okay, so let's put that in. So for phi 6, the right neighbor is 7. Okay, so that's going to be phi 7 plus phi 5, that's the left neighbor. Top neighbor was, what did we say? It was 10, right? Yeah, top neighbor was 10. Bottom neighbor is node 2. Okay, so that's phi 2 minus 4 phi 6, okay, is equal to 7 over 48. All right, and so that is the finite difference equation for node 6. All right. So, again, the reason we kind of display this in terms of the ID numbers is that, eventually, if you were to kind of carry this out all the way through, right, eventually this would make up one of the equations in your, matrix system of equations, right? And that matrix system of equation, typically you list that in terms of, what row and what column each of the indices are, right? So the ID numbers basically tell you very easily that, this equation here, first of all, it's going to be the 6th equation in our matrix, right? And we're going to have entries in column 7, column 5, column 12, column 2, and column 6. Okay. So the ID numbers are there just to help facilitate, the entry into the linear. Okay. And also just looks a lot cleaner. Okay, so let's do the same thing to node 11. So for node 11, let's do the same thing. So let's list out the ij coordinates. And so I coordinate for node 11, that's going to be 2. Okay. J coordinate for, or J index for node 11 is 2 as well. Okay. And so from that, we can compute its physical coordinates. Okay. So xi, yj. Okay. So for xi is just I multiplied by the grid spacing in the x direction, delta x. And so that is 2 times 1/2, which is 1. Okay. And then yj is the j index multiplied by the grid spacing in the y direction, which again is 1. Okay. Okay, good. All right, and then writing out our finite difference equation, we know that we're going to get contributions from every single one of node 11's neighbors. Okay. So let's go back up to our problem here and note the neighbors for node 11. Okay. So for node 11, right? Our neighbors are, we have node 10 to the left, node 12 to the right, node 7 below, and node 15 right above. Okay, so let's remember those numbers and then kind of write that in. Okay. So for node 11, our left neighbor is node 10. Okay. Our right neighbor is node 12. Okay. Our top neighbor for node 11 is node 15. Our bottom neighbor for node 11 is node 7. Okay. And of course, the central node is node 11. So that's minus phi 4 times phi 11. Okay. And then we're going to multiply that by 7/12 multiplied by xi multiplied by yj. Okay, so that's 7/12 multiplied by 1 multiplied by 1. 1 is just the identity. So, we just end up with 7/12. Okay. All right. And so that is our equation for node. Okay. So again, when you're doing these problems, it's useful to know what the ID equation is and IJ coordinates, all that stuff. You need that if you're going to be doing the programming. And you need that, to set up some things in OpenFOAM. But for these problems, I think the easier way to do it is just to look visually at your grid, see who your neighbors are, and then kind of just write those into the equations. Okay, that's kind of the fast and easy way to do that. All right, any questions on this example here? Okay, good. All right, so last thing we'll start today, we'll probably pick this up on Wednesday, is let's start to talk about the boundary conditions. Okay. All right, so if you notice, in the previous example, right, we applied our finite difference equation only to nodes that had neighbors on every single side. Right? So finite difference equations, or I say finite difference approximation of your governing differential equation. So that approximation can only be applied to what we call interior nodes. Okay? Interior nodes being nodes that have a neighbor on every single side. Because remember, you can't go beyond the confines of your domains. It's just like in the 1D case, right? So for nodes that don't have a neighbor on every side, those are going to be nodes that are on your boundary. And just like we saw in the 1D equations, our boundary nodes kind of follow a different set of rules, right? So we still need equations to specify the values of these nodes at the boundary. It's just that, instead of getting our equation from our differential equation, we're going to get that equation from the boundary conditions. Okay? Okay, so let's draw a typical domain again, and let's kind of show kind of what you would typically see. All right, so we're once again looking at our, tic-tac-toe square thing, right? Right, so in addition to a grid with numbers that you'll see in the homeworks, right? Another thing you'll be given in these problems is a boundary condition on each of the different edges of the domain, okay? Right? And so, in a very simple case, we'll have 4 boundary conditions. Okay. Right, one for each side of the domain. Okay. Now, these 4 boundary conditions, they you might have 2 of these being the same. You might have all 4 of them being different. Right, you're never going to have all 4 of them being the same, because then that's kind of boring actually. But just know that there's they can all be different. Okay, and then just like in the one-dimensional case, we have 2 different types of boundary conditions. So on the one hand, we have Dirichlet boundary conditions. So remember, Dirichlet boundary conditions, under these conditions, we are directly specifying the value of the solution for the nodes on that boundary. So for these cases, we looked at situations, we have phi at, at certain x and y, okay, is equal to phi naught, right? So these equations are very straightforward. We just, set the whatever nodal value for phi, and we set it equal to some value to whatever that boundary condition is. Okay. And then the second type of boundary condition is our Neumann boundary condition, which are our derivatives, okay? But in 2 dimensions, we put a little bit of a wrinkle here just to kind of, make it easier to interpret, okay? Right? Because remember, a Neumann boundary condition is you're basically specifying the solution derivative at the boundary. Right? In 1 dimension, though, it's pretty straightforward because there is only one direction we can take the derivative in. But in 2 dimensions, we can take derivatives in 2 different directions. So, we have to be a little bit more specific when we're talking about our Neumann boundary conditions. Okay. In reality, you can have Neumann boundary conditions in any direction, right? And so for fluids in particular, right, it's very common to have a normal derivative. So that's a derivative that's normal to whatever surface you're looking at. So that's typically a pressure type boundary condition. Another boundary condition that's very common is you have a derivative in the direction that's parallel to your face. And that would be a shear stress, boundary condition. Okay. But for our computations here, just for us, we're just going to keep it simple. We're only going to consider derivatives that are normal to the boundary. Okay. And so you'll often see the derivatives displays like this. So you have partial phi, partial n is equal to, some value here. Okay. Where this n here basically tells you that, we're taking the derivative perpendicular or normal to whichever boundary that we're looking at. Okay. So for instance, one last thing before we go, right? So if we look at our square domain here, right? And let's say that we have partial phi partial n is equal to 5 on the right-hand side here, right? So that boundary is going up and down, right? And so the derivative normal to that would be derivative in the x direction. Right, and then if you were to get a normal derivative on the horizontal one, the direction normal to this is the y direction. So you have partial phi, partial y on that face. Okay. Okay, so when we come back on Wednesday, we'll kind of expand the example that we just did to include the boundary conditions, and so you'll see what that looks like for Dirichlet and Neumann boundary conditions. Okay. The only thing tricky here is just determining the normal direction, but from there it's pretty straightforward. Okay. And then we'll get into kind of more advanced stuff in terms of unstructured grids, convection, cross-stream diffusion, all that good stuff. Okay. So thank you guys for coming today. I hope you guys have a good rest of your day, and I will see you guys on Wednesday.
You might scroll it back.
Sure. Very beginning?
Yeah, very beginning.
Okay.
Below the 2, yeah.
Yep.
Wait.
Yep.
Huh? I want a class. Why would I wait for you guys? I spent the last day of my work. My lunch, yeah. Why is there?